In this series, we're going to take a look at this Lawrence Livermore Laboratories MST-80 Rev B. It's taken me a little while to understand the difference between the Rev A and the Rev B, or the original and the Rev B. This is definitely a Rev B unit, even though it doesn't say Rev B up here on the MST-80. The tell for Rev A to Rev B is the Rev A has another socket down here with a wiring header that you configure either for hex display or octal display. The Rev B doesn't. On the Rev A, you have, like I said, that jumper block, and you have two different 1702s. One of them is the hex driver, and one of them is the octal, and you put in the appropriate ROM for the configuration you have. On the Rev B, you don't have that jumper block, and you have the ability from the keypad here to toggle back and forth. Right here, hex octal, HO will toggle you from hex octal back and forth. So I don't have the third display in here to display octal. This version of the monitor requires two ROMs, which we have here, two 1702s. There's a third one here that I assume has some user software on it. So what is this? In this introduction video. So this is a 8080 based trainer. It's got an 8080 processor. It's got, in this configuration, really two ROMs here with the monitor. So there's a total of 512 bytes there. For the monitor, it's got 1K of RAM. These are by 4 devices. I've spent some time looking at schematics. I have a schematic that I've printed out here from the manual that seems to correspond to this device to learn more about it. There's the 2112s we just discussed here. There are the two 1702 EPROM sockets here that hold the monitor. There's a user socket here. There's a footprint here for a 28-pin socket that can be jumpered to put your own ROM into. If you wanted to. The system, of course, has the 8080 processor. Well, there's an 8224 here that is the two-phase clock generator and part of the system control that's in the schematic down here. It deals with reset, sync, phase 1 and phase 2. There's an 8228, which is, I'm going to call it a memory controller. It does the decoding to generate memory read, memory write, IO read, IO write, and interrupt processing. So it's really kind of a MSI device, I guess, most likely, or maybe even an LSI device, to make interfacing to the 8080 easier. Like I say, it gives you the data bus, it gives you memory read, memory write, IO read, IO write. There's an 8205 sitting someplace in here that is really a 3-line to 8-line demux, or decoder, that is used in the end, looking at address 11 to 15 to make decisions on what block of memory is selected. So the design of this is still kind of thinking page mode. There's 256 pages of 256 bytes. So the upper 8 address bits, A8 to A15, would select the page you're on, and the lower 8 bytes would select a byte within that page. It's a 16-bit address space at 64K. But essentially, when they designed this, they were thinking pages, much like the 6502 has pages. Page 0 is where your stack and other things for the 6502 live. They're kind of thinking the same design here. So select 0, in this case, comes over here to this first 1702A, which would be this guy. Whereas the 6502 wakes up and jumps to the top of memory for the reset vector, the interrupt vector, etc. But the 6502 goes to the top of memory looking for the reset vector, and then jumps to whatever address that is for execution. So normally your ROM on a 6502 based system is up in high memory. For 8080 Z80, your ROM is down in low memory. It's at the bottom because it's the first thing the machine needs to see when it's reset. So select 0, selects this ROM, and this is the startup ROM. It's got half the monitor in it. Select 1, selects this ROM. Let's see, select 2, looks like it selects this position. For RAM, we're using select 6 and select 7, so we're really using 2 bits down here. And select 4 and 5, so let's see, select, can't see it here, 0, 1, 2, 3, 4, 5, 6, 7, so 3, 4, and 5. I don't really know where they go. they may not actually be connected to anything here. The system's using ports. So in the 8080 Z80 world, you have the concept of ports. A port, basically the lower 8 address bits, A0 to A7, can output an 8-bit value that is the port number, and then data is writing to that port. And that's what the IO read and IO write down here is. The ports are 256 locations that you can output a byte to or read a byte from that are independent of the system memory. On 6502 based systems, typically you're memory mapped. Your IO space is someplace in the physical memory space of the machine. Like I say, the 8080 Z80 have ports that are independent of memory. The machine uses port 0 and port 1. I believe a write to port 0 is the displays down here, if I remember correctly, which are captured in the schematic over here. The documentation I found online is for this variant, the MST-80B variant. What we have the schematic here for. Like I said, this board does not have the configuration jumper. It doesn't have anything in the schematic that would indicate that configuration jumper because hex and octal are software selected. The monitor grew from 256 bytes to 512 bytes, partly to accommodate that. It's pretty standard overall design. There's 4 socket positions here that appear to not be stuffed. Those are actually where the I/O lives, and we'll look at that in the manual here shortly. All of the address and data bus and all the I/O signals are brought out, and there's 10 pins on this socket that are tied to these 10 LEDs. They're just general purpose LEDs. You see it directly in the schematic here, where there's jumper 4, which is this guy, and there's pins that go through a 7404 buffer, essentially to drive the LEDs with 330 ohm current limiting resistors on them. And looking at this, see, that's tied to +5. So if I put in a 1, it gets inverted to a 0 in the LED lights. So that makes sense. A 1 coming in will light the LED up because the inverter drives the pin low. There's the current limiting resistor. So that makes sense. A 1 lights an LED. You can hook those any place you want to. In the manual it says those are most often used as part of breakpoints for debug. That would make sense. There's nothing super remarkable, I can't say the word, there's nothing really remarkable about this design. It's just a pretty stock 8080 design. The clock generator has a 9 megahertz clock coming in. I don't remember how that gets divided down, but I think that means the system is running about 1 megahertz or slightly under that even. It is designed well, in my opinion, in the fact that the address buff is fully buffered. So there's a bunch of 7407 open collector buffers, and then it's using pull-up resistors. They look like 1K pull-up resistors. So the 8080 can pull an address pin low, but it relies on the pull-up resistors to pull it high, so it's fully isolated. So that gives us really good fan out. Fan out being I can drive multiple things off this address bus. The 8228 does the same thing for the data bus and for these control signals. Again, it gives you better fan out. You can connect to multiple inputs. When you look at the RC 2014 Z80 processor, that system, they're not using any kind of line drivers, any kind of drivers like this. It's just the Z80 sitting directly on the bus, and that will eventually run into fan out issues. More typical design is to use some kind of buffering before you get onto the bus. There is a data in and data out, which must be tied to one of the socket sets up here. Again, actually it's for the keyboard, it looks like. At least part of that's for the keyboard. There's the keyboard here. There's column drivers that come off AB0, 1, and 2. Where are AB? Okay, AB0, 1, and 2 are the buffered version. So address buffered 0, address buffered 1. And it just scans through them, looks for one of the bits, does a bit of work to capture it, and then make a decision which key is pressed. These actually are really nice little switches. I found it interesting that the 0 through F are basically a little bit of tape on the cap. The enter it's completely worn off here, but it does say enter under there. It does say display under there. It's just the white's worn off. Step, hex octal, load high. So this loads the address high order byte. And then whatever you have in the display becomes the low order byte when you go ahead and hit run to execute. There's a run single step switch here that, runs the program single step, an opcode at a time, and you're using the step button here to step through your program. So why this system? There's a lot of single board systems out there in briefcases. HP made a bunch of them. There's a number of them. I became really interested in this because I've always wanted to find the briefcase system that I believe I used in college. I graduated high school in 78. Late 78, 79, I did 3/4 of college at Weber State College. It's now Weber State University in Ogden, Utah. I took classes I wanted to take, not classes in a particular, heading to an EE or a CS degree or whatever. Wasn't disciplined enough, honestly, then to have focused on a degree. I just wanted to have fun and take classes. I took a, quote, computer-aided graphics course, which I may have mentioned before wasn't much of a course. I took a digital design course, and I'm 99% sure this is the briefcase computer we used in that course. I could be wrong about that, but I'm very sure this is the system. I look at the HP ones, and they're much more complex. This is a really pretty simple system, 8080 single board computer. There's a little bit of prototyping board here. The E and L tag here that came off the back of it really, to me, speaks to the age of the system. I have a bunch of these ELI prototyping boards like this that are from the 70s. This board definitely goes back to the 70s. This paper was peeled off the back for some reason. I'm assuming there's some kind of an insulator there, so the metal contacts inside of here aren't shorting up against the metal there. I haven't removed it to see. There's a linear power supply under here. I don't know if the X means the power supply is bad. It may well. Glitch from Glitch Systems on Twitter, I believe he's the guy, or maybe, I think it was on Twitter, mentioned that he had to rebuild a power supply on one of his, and it was a linear power supply, and I'm not surprised that this would be a linear supply in that era. I'm sure it's going to be a transformer, diode bridge, or 2 diode bridges, filter capacitors, and the supply puts out +5, +12, and -12. They enter onto the board over here. There's a bit of ribbon cable underneath from the supply that solders on here. The board itself, then I need to find something to point with. No, that's not going to work well. That's way too shiny. Let's take my chip puller. The -12 comes in, and there is a Zener diode, a 5.1 volt Zener diode here in the resistor, and that generates a negative 5.1 volt rail for the system. And then the -12 is dropped through 4 diodes here. So each diode's about 0.7 volt drop. So that gives you about a 3 volt drop across all of those, which generates the -9 that the 1702s require. So like I said, there's +5, -12, +12 come in. A Zener regulator to produce the -12 rail, and a set of 4 diodes that use diode, the forward voltage drop to basically get you the -9 volts. Well, that's what it does. Everything else here is just regular old TTL logic. Let's see if we can pull some date codes off of things without getting my head in the way. 9th week is 78 on that resistor pack. 35th week is 77. 10th week is 75. 22nd week is 74. I have no clue. 44th week of maybe 78. I'm guessing that's not a date code, 3193. 31st week of 93 seems awful late for an 8080 processor. 20th week of 77. 44th week of 78, I believe. Early 78. So you can see from the dates here, this is a mid to late 70s load. So, and again, there was the MST-80 that was originally released, it looks like in about 75, quickly followed by the MST-80B in 77, 78, sometime in there. So moving forward, what are we going to do here? Well, I'm going to remove the board. I'm going to remove the power supply. I'm going to go through the power supply, make sure it works, do a bit of loading on it to make sure it works. I at some point will pull at least the rare stuff on here, if not the entire system, down to the bare sockets and check power rails. I believe I have a third LED package that can be put in here for the third LED, so I can actually use the hex octal switching. I think that would be really cool. So once the voltage rails are verified, it'll be put the components back in, bring the system up, and see if it runs. I have some concerns that the 1702s have lost some bits or have gotten weak, although the case has been closed the vast majority of the time, so they've set in the dark. So maybe it hasn't. It's really clean inside. There's very little dust or dirt in here. There's a little bit of collected dust right here around this nut that I'm breaking loose here. And there's some on this one as well that kind of to me says this thing at some point was probably fairly dirty inside, though I don't know that. I don't think that's the remains of like a washer. Well, you know what? That might be the remains of some kind of fiber. No, the more I look at that, the more I think that is dead silicone that was maybe used to hold the nut in place. Yeah, the way that just stretched, that is just old dead silicone. Good, that makes me happy. I was thinking it was just accumulated dust, and being silicone makes a lot more sense to me. So there may have been like a silicone washer or just a little ring of silicone put down there to keep the nut from turning. So that again speaks to me that the system has been left closed. I will deal with that. One of the National Archives has a bunch of documents for the original MST-80 design documents, drill guides for the case, etc. that they just haven't scanned. They're not available as download. I'd love to get my hands on those at some point. I don't know if I'll be able to or when I'll even approach that. The chip in the socket here is a 1488, so that's either an RS-232 line driver or receiver. The 1488, 1489 pair are EIA level receiver drivers that convert to TTL. The system and the fully configured system came with a parts kit that included a UART and a bunch of other parts for experiments. I'd love to find the books that go with the experiments. I have the parts list here. I don't have the actual experimental books. It'd be really cool to find those at some point. Yeah, put the line cord back in. The line cord is in excellent shape. Every picture I have seen of this seems to be a round line cord. This is a flat, so it's a little bit different. I've not spotted one yet with actual solder mask on the board. There are blue boards and there are brown boards, and then a closer look at the blue boards, I assume those were solder masked or not. It's just the material is a blue, whatever the material is for the board is blue. So this particular one, when it showed up on eBay, there were several of these that popped up at the same time. They went on sale. He discounted them pretty substantially, and that's why I jumped on one. And the reason I jumped on this particular one, and we'll look at it here, is in the picture, I could see there was documentation with this one, and there didn't seem to be documentation with the others. This tag I found in the back of the briefcase here. The documentation was in the back. There is a schematic here in fairly decent shape. And there's been some handwriting to fill stuff in. This is identical to the one I printed out. As far as I can tell looking at it, I think it's really the same schematic. I guess we can tell maybe down here. 4174, 4174. God, is the date really that old? I don't know when the system was actually introduced. Or maybe that's not a 4, that's hard to read. 479, 976. So they are different. This is 976. This is 479. So they are different versions. Yeah, M&M, M&H. So there are changes between these. Oh, this goes to Rev C. So there's Rev A, B, and this one's Rev C. So again, the manual I found online is a little newer than the manual that came with this. It's Rev C. I don't know what the schematic changes are. I'll have to maybe analyze this at some point to figure it out. But this should be the schematic that goes with the system I had here, and that's really cool. There's the MST-80 User's Manual, kit number 2. Up here is a piece of tape that looks to read N arrow pointing to L and 8 arrow pointing to H. I have no idea what that is. I want to get that removed from there, and hopefully the tacky, the glue, whatever it is in the back of the masking tape, cleaned up. This looks to be a fairly early version of the manual. The later ones have a blue cover and Lawrence Livermore Labs, and maybe that was just left off this. I don't know for sure, but for some reason this one's bound. It's in decent shape. It's single-sided, which I really like, meaning it should print well. Dale Curtin, it'd be awesome if you were out there and spotted this. In 1982, created this square wave. So program generates a square wave signal at output port 01 with period of 62 and 30 B times 1.0 microseconds, where B is the decimal value of the register on entering loop 1. Okay. When connected to an amplifier and speaker, the microcomputer generates a tone or frequency 1 over period. So that's interesting. So it's a square wave generator that is programmable for tone. We're going to have to keep this in mind because there's some other stuff here that I've already tweeted a bit about. It's going to be really interesting to look at. There's a symbol table, etc., from an assembly output here. The assembly output is the monitor itself. Starts on this page. It is dated 8/23/76, written by Gordon Jones, modified by Ken Muchow, I don't know how to pronounce it, in 78. I love this comment here. Why? Load A key temp, probably like a keyboard temp holding. Move C to A, out 0, put 001 display, go to key routine, get back to key routine. Why are no ones, then go, then 0 flag set? Are no ones, then 0 flag set? Interesting comment. You know, somebody has looked at this and in pencil has marked it up a bit. That's really interesting. So things that they thought were important. It's cool that this was used. I like that. I like that it's bound. It's just kind of a neat artifact. We then have, we'll have to look at this. We have a program, and this is what I tweeted about, some pictures of this, DAISY program. And if you look at the data here the program consumes, it's Daisy, Daisy, give me your answer due. I'm half crazy, all for the love of you. It won't be a stylish marriage. I can't afford a carriage. But you'll look sweet up on the seat of a bicycle built for two. So I'm assuming, well, I'm not assuming, it's got to play the song. The code here is written to pull back or to grab each byte out of the data set and then use it as basically a delay to produce tones. Now, I don't, if we look at that program we saw on the last page here, we actually see an out command, so out 0 So that's where he's setting the bit out to port 1 to toggle up and down to produce the sound. There is no out command in this one. So it's not outputting a bit to a port to generate the sound. That really makes me believe this plays music by setting an AM radio close to the system, and the RF noise the system generates becomes the song. That was really common with the early machines. I think the Altair, it was discovered with the Altair. I think back in the day you could do this. So I'm guessing that's how this works, is it relies on RF noise, because nothing is RF shielded here, to induce a signal based, well, into an AM radio to produce sound. So we will at some point play with this. I've looked at the code. The code's pretty straightforward. The data set ends in an FF. There is a comparison in here that compare immediate FF. If it's found that byte, it then restarts over. So I can put the code in. I can put in a few of the delays for the audio loop and just throw an FF in and test this without having to type all of this in. So it'll be pretty easy to test this, and when I get it working, put all of the audio in, or all of the data in. Notice there's no I/O on this beyond the keyboard and the display. There's no way to save a program. There's no way to load it from anywhere. There's no serial port. There's no, nothing here that you could use immediately to save and load programs. And I remember that from the college course where we were using programmer pads like these, maybe even these identical ones, to write out our opcodes, look them up in a lookup table to generate the machine code. And this is what I call machine language programming, not assembly programming. We're not using an assembler. On Twitter, I've argued this with a couple of people. In my belief, assembly language is using an actual assembler. I'm using a computer to assemble opcodes into machine code into the bytes, and then have a way of loading that into the machine, whether it's off paper tape or whatever. Where when I think of machine code, I'm doing that translation by hand. I'm doing address locations by hand. So like label 2 here at address 0610, there's going to be a reference to that along here, 0610. So jump if non-zero to L2. So somebody had to say, this is at address 0610 and put those 2 bytes in there. It was all hand calculated. And then in this case, it's punched in from a keyboard. It can be toggled in from a front panel from switches. I consider that machine code because effectively you're very low level down in the machine. You're in your head assembling the code. You're not using an external assembler. I do not remember us having an assembler of any kind. The university at the time, my memory is it was running a DEC 10, running, I want to say, TOPS 10. There was a computer center in the basement of one of the buildings. It was a ton of VT52 terminals. It was very dark in there. And all I have ever observed in there was people playing Star Trek. I'm sure there was other stuff going on, but that's what I observed, including me playing some Star Trek. There's some example delay routines here. Commented. I love the comments. There's 3 different ones here, it looks like. There's delay loop, delay loop, delay loop. So, maybe much more optimized. I don't know. I'd have to look at these. It's interesting. They're up in address space 650. 650 overlaps with the data here. So there's 0650 right there, meaning this wasn't meant to go with this. This is something independent of this. There's another programmer sheet here. It looks like it's been copied and copied and copied. Speaker test. So this is what we saw in the manual. It's exactly what was in the manual. The out 01. There's a flow chart for it. So I love this whole documentation like this. I love the fact, I just noticed the tag here, 59 cents each for the binder. I don't see anything on here that looks like it's a date, however, but it's still, 59 cents for the binder. You could probably still get one of these for about that price today. We then have an MST-80B manual. The online ones I've seen have a green cover. Did I actually bring one up with me? I guess I don't. I printed them out. This is Lawrence Livermore Labs, and it looks to me like those are preliminary versions. And here's the one that was finally handed out in class. Notice how beautiful a print this is. The pages are still nice and white. The text is very dark. Everything is nice and square. This will scan very well, and I will scan this document. This reads very much like the other 2 that we see up. I've been able to find a download. Abstract, introduction, hardware features, 512 bytes of RAM. Well, I swear we've got 1K here. Maybe this is only 512 bytes. These might be 1K with 4 outputs, 256 bytes by 4. I might be wrong. That might be a total of 512 bytes. Which actually it has to be now that I think about it, and I'll explain why that has to be the case. At least why I think that has to be the case. 11, 13, 14, 15. A12 doesn't come in here. Oh, there's AB12. So 12, 13, 14, and 15 come into the device here. So that's going to select. Thinking this through, I wish I could explain it better. I believe these are 256 byte selects. I partly say that because the 1702 EPROM is 256 bytes of data. It's how big is it? It's, what's that? 2K by 8. It's got to be a 2K device. 2K divided by 8 would be 256 bytes. It has 7 addresses, A0 to A7, so there's 8 addresses. Actually, it has 8 addresses coming in, so it can contain 256 bytes. And there is select 0, select 1, and select 2. And select 0, 1, and 2 are coming off this 8205 here, meaning each one of these selects is selecting 256 bytes onto the bus. Select 6 and 7 down here are going to be the same configuration. Each one's going to select 256 bytes, meaning these 2112s, I guess I should look them up, have to be providing 256 nibbles on this one, 256 nibbles on this one to get 256 bytes, and together you get 512 bytes. So the system's 512 bytes. So when I said it was 1K earlier, I lied. Sue me, I guess. So that confirms to me there's only 512 bytes of RAM, which back in the day seemed like a lot. Not so much. It says it should have a 3-digit display here. Maybe one of the displays has been removed for some other project and they only run it in hex mode. 10 uncommitted LEDs, which we have here, including a monitor program, hex oct monitor, excuse me, because you can toggle hex and octal right here. Talks about the keypad. How subscript 8 indicates an octal. Remember, octal numbers are 3 digits, so octal numbers run from 000 to 3FF. 3FF, Jesus. Run from 000 to 377, and if you count the number of bits in the 377, it's going to be 2 bits, 3 bits, 3 bits, you get 8 bits. The machine in octal mode is really going to be split octal, and what I mean by that is when I put the high order address in, if I was going to put the top memory address in, I would enter 377, load high, and that would load the upper byte of the address space, and then I would enter 377 again on the display here, and that would in the end generate an address of all ones onto the machine, but it's 377, 377 for the lower byte. So it's not like 177777, which would be a full 16-bit field. The 2 bytes are split apart. That's split octal, 377, 377. And you know, all the early devices thought this way. The original Heathkit H8 was a split octal machine as well. There's reasons that makes a lot of sense in some ways when you look at the opcode structure of the 8080. In split octal, the bit patterns for the 3 locations can give you really good information on what register is a source, what register is destination, some of that kind of stuff. There's of course an enter to enter data. There's an examine to examine location. We will, once we get the thing powered up, play with all of this. Monitor subroutines is a call from a user program, really typical. We saw this on the OSI board with a 65A monitor and with the TIM monitor, where you can call into the monitor to like get a key from the keyboard or a byte from the UART in their case, etc. So you know, there's a little example program. Again, this manual is just in excellent condition. This is going to scan really well. I will do what I always do, and that's manually clean up the pages, remove fly marks. Things like this will get removed. There's a little dot over here from the printing process on all the pages. It'll get removed. I like to clean up the pages. When I do that work, I tend to reproduce missing text. I really don't see any missing text on any of these, which is nice. This is a really good printed copy of the manual. Although you get to this photo here, and you can tell that it's, you know, it is a reproduced. Don't know if this is a photocopied manual Maybe it is, maybe it isn't. However it was produced, it made a nice dark image. Picture of the system, as we've described it: power supply, breadboard, display, blah, 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 blah. There it is. A little closer up view of the keypad. You can see where it actually said enter and display here. Obviously, those are the most run, or the most used. Enter. I'm assuming when I do an examine a location, I can then use enter to move through memory and look at all the bytes after it. That's my assumption about how the monitor works. So that would become the most used key. So the system definitely saw some use, just because the enter is rubbed off there. I don't know. I can see where enter is kind of stamped into the plastic. I don't know that I could ink fill that back and make that show up, or paint fill that. I don't honestly know. Don't know if I'll even try. In this photo, they of course show a 28-pin socket in the location down here. We don't have that socket. These look like they're machine pin sockets based on what I see for these. For the processor, obviously I don't have machine pin sockets here. These are also not 0 and 4 or 0 insertion 4 sockets as far as I can tell. Although I may have to play a bit. What does that center look like it can move? I guess it can't. Well, I'll find out as we dig deeper. Well, if I can get the page to flip. I honestly can't get the page to flip. Block diagram of the system, just what I've described here. You know, there's a single step and a run switch. You run and single step over here. There's the ability to single step through code. There's a processor. There's the control chip here. The 8224, the clock generator, reset, the reset switch, wherever reset is, talks to that chip, which then resets the system. Port, in and out, RAM, ROM. It's a pretty basic little system. There's a much smaller version of the schematic, but this is a real high quality version of the schematic here. Nothing's faded in it as far as I can see. It's very readable. It's not like a smeared photocopy. And again, at 600 DPI, that may copy really, really well. I'd mentioned these before. There's the 4 empty sockets over here. This is those 4 locations. So there's an I/O location, an address, data and statistics, and lights and control. And looking at the lights and control, you can see it runs light 1 and loops around to light 8. So this would be light 1 to 8, and of course 1 to 1, light 2 to pin 2. Data bus is sitting here. Memory read, memory write, I/O read and write, etc. are all up here. Select 3 and 4, which are being brought out. Now I know where those go. Select 3 and 4 off the address block selector here are actually brought out so that you can talk to external memory perhaps. So that's cool. Those are brought out. Select 3 and select 4. Data buffered. So these are DB. And there's data 0 to 7 for I/O. So there's data bus, and then there's port I/O out and I/O in. So I/O read, I/O write are going to talk to this socket. Memory read write, it looks like to me, are going to talk to this socket. And they both are going to share the address space here, A0 to A15. In the case of ports, there's only 256 ports available, so it only reads about A0 to A7. For RAM, you need all 16 address pins to get 64K of RAM. Interrupt request, interrupt, wait, hold, HLDA, hold, I don't remember, ready. So pretty standard stuff. The flowchart for the hex octal monitor, again printed really well. That should scan very nice. The actual memory map of the system. So page 0. 1 and 2, which are these 3 proms, uncommitted page on 3 and 4. So 3 and 4, remember, were brought out here. Page 5 is the keyboard. So keyboard's actually memory mapped. It is not on a port. That's an important consideration. Page 6 and 7 are the blocks of RAM. And again, looking at the addresses here, 0600 to 06FF, that's 256 bytes. That confirms. That's 256 bytes total between those two, and 256 bytes here. That reconfirms it's got 512 bytes of RAM. So page 6 is RAM, page 7 is register, storage, and stack. So on the 8080 and Z80, you set a stack pointer where you want the stack pointer to be in memory. It does, it's not a fixed location like I believe it is in the 6502. You can set it wherever you want to, and you traditionally set it up at the top of your highest RAM on the system, and then the stack grows down from there. And that's what they've done here. I suspect we'll find the stack is at 007377 or address 07FF. I suspect that'll be the top of the stack. We could probably look at the assembly listing and actually determine that. Keyboard. Let's see if we can see anything here that gives us a hint. Load stack pointer was 07F0, so I'm a little bit off there. 07F0 is going to be 16 bytes down from the absolute top of RAM. So the stack pointer is a little lower in the memory space than my guess. That means there's something in those 8 or 16 bytes above this. And there's something above this in those 16 bytes. The stack grows down, doesn't grow up. It grows down in memory, as at least I'm 99% sure it does. I've looked at too many processors recently. So anyhow, really nice clean memory map. Page 7, there it is. There's the breakout of the so the memory mapped I/O. There's the breakout of the locations. So the octal and hex addresses, current value of display. Sweet. So it's just memory addressable for the keyboard. That's pretty cool. Flowchart for the program I had mentioned earlier, and we'll look at this again if I can pick one of these up. But back at the time I was doing this kind of stuff, you wrote out your mnemonics, LXI H 0640, so we know it's going to talk to address 0640. It's going to load immediate H, the byte at this value. So LXI, if we worked our way through here, LXI H looks to be, it uses 10 cycles. It doesn't actually give me, well, it does give me the opcode. 2-1, there's 2-1 right there. So the opcode's listed in binary, and then here, right there, it's in hex. But yeah, that LXIH is a 2-1. So literally, that's what you were hand assembling. You were looking them up in some kind of a lookup to come up with the bit pattern. There's a better printed version of this sitting here in alphabetical order. It looks like there's LXIH, which again is 2-1 hex, and it takes a 16-bit data value. So D16 means a 16-bit data value. 0640 would be a 16-bit data value. That happens to be the address it's going to look at. Pull the byte from that address. This is going to load hex 1C into the H register. So this is how, for me, back in the day, I learned how to do this, was you were writing out your opcodes, you were hand assembling, hand figuring out where labels were for jumps, those kind of things, hand laying out data sets if you needed to do data. I call that machine code programming. I don't mean with machine code it is microcode. That's something different in the processor. And I'm not using an assembler, which is why I don't call it assembly language. Numerical listing. So this is really nice they've done this way. There is the bit patterns. There is an alphabetic listing of opcodes from ACI to reset 3. There is then the numeric listing from 0002. So we could look in here for 1C hex. We would find 1C hex. Actually, I'm way past it. 1C, there it is. Oh, 2-1 hex. How did I get 1C? 2-1 hex. That's why it looks funny. 2-1 hex, there it is. We look up 2. Oh, I'm pointing at the wrong place. 2-1 hex. 2-1 hex. 2-1 hex is a load immediate H with from a D16 address. So again, you had multiple pages to be able to look things up. Essentially, this is a disassembly sheet. I can look at an opcode pattern like 1-9 here. I can go down the stream here and 1-9-6. 719 That doesn't make sense. Oh, that's location. Opcode is a C3. I happen to know C3 is a jump, and it's a jump here. But if I find C3 in the sheet, C3, it's jump address. It's just it's a jump. It's always going to jump. It's not like a jump non-zero or a jump 0. And then we get into the actual program listing. But you essentially had a way of manually unassembling, getting back to the opcodes, a way of assembling manually. And you could do it on a programming sheet like this. This very much harkens back to the early days of computer science. In a lot of ways, this is how early versions of the Apollo software for the LEM was written. Back in the day, it just wasn't. It was a common practice. It's just how things worked. And then assemblers were invented, and it became easier to do. It's actually a really nice scan as well of the assembly, the assembler output when this was assembled. Pretty readable, considering that was a document probably looking at the typeface printed on a teletype. It's 100% uppercase, which is not surprising from back in the era. Looking at the font, I'll call it the font, this looks very reminiscent to me of a teletype output, which would make absolute sense. So, very cool. So we've kind of looked through the manuals. We've taken a look at the hardware. We've talked about moving forward, what documentation I have. We've talked briefly about the board. We'll get into more detail. I love all the 0.1 microfarad. I assume they're 0.1s. All the spiking caps here. There's a nice sea of them. Every TTL IC, every TTL IC has one. That's a resistor pack. 4 TTL devices, 4 TTL, or 4 the spiking caps. And this one just happens to be between the resistor pack and here. The resistor pack here doesn't have one. The pack here doesn't have one. But every TTL IC, well, nearly every one. There's a few here that don't. Ultimately, there's one close to all of the SRAMs. There's definitely one. Some close to the 1702s. The 1702s are interesting because there's no ground pin. The device operates on +5 and -9. And the first time you encounter a 1702 in a schematic, and look, you do a whole lot of head scratching going, where's the ground pin? Where's the ground pin? You'll see this in the schematic. There's -9 on pin 16 and 24, and there's +5 on 23, 22, 15, 13, and 12. And that's because those pins also get really bizarre voltages put on them for programming. Along with the address and the data. Programming in 1702 is a really interesting and bizarre sequence of odd voltages. And but anyhow, the part uses -9 and +5. There's no VSS. And the part basically on the outputs generates, an output that is 5 volts below +5 to get to a ground. And this is a concept in digital electronics you probably need to wrap your head around if you don't understand it. Between the -9 and the +5, you can find a position in there, voltage-wise, that is as compared to the actual ground coming into the machine. So all these pins here are ground, or even the power input module down here, there's a ground line coming in. You can find a voltage between -5 or -9 and +5 that is the same voltage level, basically it's this ground, and that becomes the 0 coming out of the device. So ground is nothing magical. It's a reference point that you measure other things from, and that's something people have a hard time wrapping their head around. The fact that there's a black lead on this meter doesn't mean this lead is ground. It means this is a reference that I am measuring the red lead against when I'm in voltage mode. That's why when you get the probes like backwards on a battery, it'll read -1.5 volts rather than +1.5. This lead is being measured in reference to this one. And ground is not anything magical in a circuit like this. It can indicate all the way back to earth, ground, those kind of things. But it's a common reference point that everything else is referenced against. That's a concept that some people really struggle with. I could run a TTL logic with 100 volts on VSS and 105 volts on VCC, and the logic would work just fine. It just needs a 5-volt potential to run. So that's why these 1702 EPROMs can get away with that, is they are designed sufficiently to output something in the middle here is 0 volts for a 0 out and near +5 for a 1 out. Hopefully that's not too confusing, and it's way off, way off what I meant to be doing in this video. So sorry for the rat trail there, or whatever you want to call it. I think I've covered everything. I think I've talked to everything I plan to talk to. This is going to be fun. I suspect it probably works as is, unless the power supply has issues. If not, I have sufficient, definitely have all the parts that are in here, and I have a way of programming 1702s. Actually, I have a couple different ways that if I needed to program up a set, because I thought these had failed, I could do it. I could also probably ask Glitch of Glitch Systems to program me up a set, and I suspect he would as well. I don't think there's much else to say here. It's a very nice little system. I keep finding things to talk to. These are electrolytic capacitors in the power supply circuit. Over here, there's a bunch of electrolytics in here. These are really old electrolytics. They go back to the 70s. These probably should be replaced just as a general thing to do. They all look like they're 5 microfarad, so 5 μF. I think it's a mu, or it's a micro, 5 microfarad, 25 volt. Modern one would be 4.7 microfarad. Back in the day, there was, more solid values, or more integer values, I'll put it that way. So these could be replaced with 4.7 microfarad. I've noticed on the board that Glitch cleaned up and reworked and sold recently that he put tantalums in here. That would be appropriate. I hear a dog coming up the stairs to join me. Yep, there's Anna. She's coming to join me. She misses Daisy, as do I. I had to put Daisy down. She finally got so ill from the Cushing's that I had to put her down. It was right before Thanksgiving. Anna gets pretty lonely downstairs alone when I'm up here, so she has to come up and visit. Other things to talk to. You know how I am. I keep finding things. I have no idea what that logo is. I don't know. Maybe it's part of the Lawrence Livermore Laboratories logoing. Anyhow, let me shut up here and end this video, or I'll just yap on the rest of the day. Hope you enjoyed this. If you got this far, I appreciate it. Like if you think it's worthy of a like. Subscribe if you haven't and you enjoy the channel. And we'll talk soon.